University. Hongkai got his PhD from UCLA under the supervision of Bjorn Enquist, I believe. And then he was a postdoc at Stanford before joining the faculty at UC Irvine. And I met Hongkai while he was chair of the math department. We overlapped there at UC Irvine. And so now we're happy to have Hongkai now coming to us from Duke, and he's going to tell us about model complexity and its implications.
Okay, Tom, thank you for the introduction, and thank the organizing committee for the invitation. Unfortunately, this is a special time, but fortunately, Zoom or this kind of virtual technology makes this kind of meeting practical, and I think it's unique and interesting experience. I hope this won't be the forever format for the rest of the time, for the future. Okay, today I'm going to talk about something I try to, I define the model complexity and try to see what it implies when we try to solve a problem. And this work is partially supported by an SF grant. Okay, so when I define, so if you have a set of objects you want to study, for example, the set could be a set of points, vectors in high dimensions, or it could be a set of solutions for PDEs, could be a random field where you can think of it's a family of random variables. When you study such set of things, although it maybe looks complicated, maybe it is complicated. When I say it, how do I kind of characterize this? It's rather intrinsically complicated. It's just because you choose the wrong embedding or representation and it looks messy. Here we say, if we characterize a set, okay, S, which in a metric space, we say we characterize its richness, extent, whatever, by the dimension of the best linear space. So I'm talking about linear approximation, the best linear space that can approximate a set S to certain error, okay? You give the error, I want to see what is the minimum dimension of a linear space if I want to approximate this set uniformly to that accuracy. So for example, if I have, I can only draw 3D, so but it could, in this set of point could be high, live in 1,000 dimensions, but eventually it's really close to a two-dimensional plane, okay? And then you really want to find whether there's such a low-dimensional structure. If you do, then the next step is how you find it. It may not be an easy job, but at least give you a hope you can do that and you can do effective dimension reduction. This is this characterization is kind of due to the Kolmogorov Unwis, which people have used in information theory and many other disciplines, is trying to see the kind of dual question. If I give you a set, you want to see what is distance to the best n-dimensional linear space. Okay, so we're saying given the error, what's the minimum dimension you have to use to approximate that well? The other thing is, if I give you, I can only deal with n dimension, what is the least error I have to make? Okay, so that's something kind of due to each other. The implication, so I say if I have this, there are quite some implications, few implications. First of all, I say this characterization is intrinsic in the two sense. If you're talking about a sparse representation, if you rotate an orthonormal transformation, like a rotation, will destroy the sparsity. But this dimension, okay, intrinsic characterization doesn't depend on orthonormal transformation. Also, it's the best space, linear space. So you have to use the best representation. So if you happen to have the wrong one, it doesn't mean anything. So you have to say it's really the intrinsic, so really how rich it is, using the best linear space approximation or best representation. So if you see, yes, there's a low dimensional structure, that means given epsilon and epsilon either very low or grows very slowly with epsilon, then this is some problem. You have good hope to do dimension reduction, model reduction, whatever you can do. You can do something, and this can help you in computation, in representation, whatever. But as I said, you still have the challenge to find a good representation or the basis of that space. But in general, you have the hope, you can work on that. If not, then that means no matter what you use, a deep neural network, whatever, if it's truly high dimension, this won't be effective. But if there's a low dimension, you can use different approaches. Maybe if you want to use a nonlinear parameterization, deep neural network could be one. But if it's a true high dimension, then first of all, if you really want to approximate well, have good generalization property, then you have to have enough parameters, or you have to reduce, put some constraint to reduce the dimension. So it tells you what approaches you should use, whether you use also, if it has a low dimensional structure, maybe you have to, and the problem is complicated, maybe instead of using a priori given basis, like wavelet, Fourier, or finite element, maybe you want to use some problem-specific basis to just reduce the dimension of the problem. Okay, so another thing is, you know, when we studied this, we give you kind of some hint or give you some clue or insight, say what kind of things can make the intrinsic dimension high or could cause richness or something like that, or what helps you to see they're probably a low dimensional structure. So usually if you want to, one thing a lot of people already utilized explicitly or implicitly is a smoothness, regularity. That's definitely true. That will help you to reduce the, usually the intrinsic dimension if you have a smooth dependent on things. The other thing is less obvious. So we will try to see different ways where we can still have this low dimensional structure, or in cases there's mechanism prevent this from happening. Okay, let's start from a very simple, well, recognized partial differential equation. I start with PDE model, but usually I can start with random vectors, but let me just start with the PDE problem first. So this is a very familiar looking elliptic problem, and I enforce coercivity. So A is positive, bounded below, bounded above, but I do not assume any regularity of A. So it could be L infinity. So still the solution here exists, and you may not look at all that regular because the A can be really wild. It looks like can be still very messy problem, but you will see actually it is not. So I'm saying what's the implication? So I'm trying to say when I start this, where do I start from? Okay, so if I want to study how rich the solution to this type of PDE is, or how bad the, how good or well or ill conditioned for the inverse problem, we can always start from something we're familiar with. So let's see, this is, so if we want to solve the forward problem, give F, G, and A, then so that's the forward problem. And the inverse problem is basically saying, this is the usual linear given FGA, how do I find U, okay? We know for this type problem, there are a lot of efficient algorithms still, but for when A is multi-scale, this is something not that trivial. Inverse problem, also, we have inverse problem related to this, like EIT. When I give the a different voltage at the boundary, then I measure what the current output. And then from this relation, I want to infer or recover A. Or nowadays, there's about uncertainty quantification. If my A depends on random variables, is a random field, then you want from the solutions you have, you want to infer, it's kind of inverse, but it's parametrized in some way. So you want to infer the statistics or some sampling of this parameter A. Okay, so here comes the first key things that what we should study, what we should be looking at. So we start, it's not very surprising, the Green's function or the fundamental solution, saying if I give impulse at location Y, what my solution looks like. Okay, so basically you can think of the position of the source is the parameter, is a parameterization of the family of solutions. So you give me Y, what the solution looks like in the whole domain. Okay, so by maybe first year graduate course in very beginning, I think, the PD course, you know, U can be represented as in this form. So if you look at carefully what it says, no matter what F you give me, it's nothing, it's a superposition of this Green's function. You can think of, I have these strands of sources, a location Y, and you superpose all these sources together to get U. Okay, here a little bit more complicated, but it's related to G. So what it says, when you're varying right-hand side F, all the set of solution is a superposition of the Green's function. So in a sense, if I want to see how rich the solution is, I can see how rich this set of function. As I said, I'm now looking at the G of X, Y as a family function of X, a family of function in X. And this family is parameterized Y. Basically, by putting the sources at different locations, is the solution forms a big set, very rich, or there's some low dimension structure in there. Of course, I said with some epsilon error, you cannot see accurate representation, then it is infinite. It is even uncountable. But I'm saying if, okay, wire this Y, if I give you some tolerance of approximation, is this family of function rich or not? If that is rich, then the solution is rich. If this is not rich, the solution set is not rich. If you're talking about inverse problem, it's mainly trying to do the opposite. So this is your true solution. And this is my perturbed solution by, I have a guess of the parameters. And then I look at the difference of these two. That's the observation I can have. And I want to find the observation of the difference in the solution, okay? I want to infer what is the perturbation in the parameter. If you do a simple manipulation, you will find there's a relation between the perturbation in the solution and the perturbation in the parameters. And they're related by this equation. And eventually it's related by, again, this similar integral formulation. So basically your perturbation, okay, is propagated or reflected in the perturbation of this delta U by the Green's function, okay? So if your Green's function is not rich, so which means a lot of perturbation will be compressed by this convolution. Okay, so which means what you observe is a compressed version of what's the true perturbation here. And that means this problem is very ill-posed because many things are compressed. If this is not compressing, okay, then you would say, okay, this probably, you do have enough information. So it tells you, how much information from the perturbation of the parameter can be measured and felt with some tolerance epsilon. That's usually determined by your noise level in your observation. Of course, if you solve this, it's much harder because G depends on delta A too, because G depends on A. If you have A plus delta A, to recover A, you have to know the delta A. So this is a really nonlinear equation of delta A, but still the qualitative behavior of the Green's function, how richness is, tells you, I mean, resolution, how much information you have, and so on and so forth. You can infer from this relation. Inverse problem in the set, I already mentioned this, of U due to the perturbation in A is also a superposition of some Green's function. A known Green's function, but it's still true, the case. So, no surprising, Green's function is the building block for PDE model. So, really by studying how rich, okay, so from now on, for the PDE model, I'm trying to study the Green's function by a family of by regarding at a family of function in X, parameterized by your location of sources. How rich is this family of function in X? Okay. So this is closely related to another property of Green's function, which is actually it's the same. We can study, which is another way of saying how complicated or how rich this family of function is, or how complicated this two variable function is. So basically, you're trying to see, okay, if I give you a two variable function, how many, if I want to represent it as the sum of product of one variable function called separability, at least how many terms I need in order this approximation less or than equal to some tolerance. Again, you see, in general, this is if it's intrinsically two variable function, and the variation in x, y, I can, as wild as can be, and this cannot be small. But if this is, you know, not too far from one-dimensional, two-dimensional, three-dimensional function, then what it says, you know, this n epsilon can be 2, 3, 4, and then you can find appropriate, of course, find the appropriate FLGL is a big challenge too, but at least you know you can approximate it by a few separable representation. If you look carefully, this is really look like this is your matrix, infinite dimensional matrix, whether you have a low rank approximation. Okay, X is one direction, Y is another direction. So the question is whether this has a low rank approximation. You can think in that way. But this is what we're talking about, two variable function. And what I'm trying to say is this is exactly related to what I said, the characterization of the intrinsic complexity of the family, the Green's function, or the family of function parameterize this, because this is the basis. Well, this is the coefficient, depend on where you are, and then the coefficient changing. But basically, this whole family of function in X can be represented by linear combination of FL, this many functions. So that's FL form a linear space, and that linear space can approximate this family of function in X uniformly well. And again, this is, I just put it in any norm, but most of the talk, I'm just talking about L2 norm because that's exactly corresponding to SVD or low rank decomposition of a matrix in computation. That's what you do. Okay, so again, the N epsilon really manifests the model complexity of the PD. So I'm trying to either talking about how separable this is, approximately separable this is, like how, whether you can immediately see whether it's a low rank approximation if I discretize these things, or the intrinsic complexity in the sense of how rich the solution of the PD can be by knowing how rich by why, how many things you can do. I know another way of saying this, I think intuition is saying basically, if I give you the Green's function at neighborhood location y, can I infer the Green function at my point? Okay. If you can, that means this is not very rich because I only know a few, then I can interpolate, I can find, this is all this kind of, in linear algebra, you use certain columns to approximate the whole columns. This is exactly also related to that. So can I use the Green's function at a few locations, nearby location to infer my Green's function located in my place, or how closeness that means. If it has to be very close, that means very rich. If it is very far away, I still can interpolate my location's Green's function. That means it's not rich. Okay, so previous work, there are quite a lot, because this is directly related to developing fast algorithms, and quite a lot of study on this. Most of the time, people in the old days, most popular approach is to show it is separable, and for separable, highly separable, you just have to construct approximation. Okay, and most of the time, it's using the very well-known either polynomial basis, or you use that FL basis is polynomials, or it could be Fourier basis, and so on and so forth. Then you basically have to know the explicit expression of the Green's function and trying to expand it and using some analyticity. And you can see the expansion converges very quickly. Then that's polynomial give you a separable expression, a constructed way to show it is highly separable. Although the optimal n epsilon, which I try to emphasize, because later we'll try to use this, the optimal n epsilon may be far away from the particular basis you choose. Although you show it is highly separable, but that representation you choose may not be the best one. And to find the best one, that involves some work, and see whether it's worthwhile to do that, we'll see later. For example, fast multiple is basically by using the polynomial basis, you already know how to compute those coefficients very fast. So that's a good thing. But again, for some problem, that number of terms you used in that expression may not be the minimum terms. Interesting work is by Bemidov and Hackbush in 2003. They proved for the model problem I showed, as long as this is L infinity coefficient, and it's coercive, and then you see the n epsilon grows very, very slowly. Log of epsilon d to the minus plus 1, d is the dimension. So maybe the solution looked very wild for this multi-scale AIJ and so on and so forth, but you have a hope that the solution or the Green's function stay near a low dimensional manifold. Okay, also homogenization, all these things, try to find that in analytical way, but also we can do numerically to find that, but it tells you it's highly separable. And that's why elliptic problem, there are so many different efficient solvers. We'll mention a little bit more in the future, in the later slide, but in general, it's intrinsically not that complex. Even the AIJ in L infinity looks very wild. The key things is the Cacciopoli inequality, which is somehow gives some regularity. It's like the inverse of Poincare inequality, is bound the gradient U in terms of U. By compromise a little bit, you enlarge the domain of U, the L2 normal U is in a little bit larger domain, and the gradient U you bound is in a subdomain. And you can do that. So that's the key things to me to show why elliptic problems like this coercive one solution space is not that rich. Okay, you still have this. You don't have analyticity, you don't have anything, but you just have this, you can show this. I think it's a very interesting non-constructive way to show this. So high separability, one direct use is to showing if you do integral equations, which is convolution of some kernel, which is many times is Green's function, many times is other type of things. If you have low rank approximation, then the matrix may be dense. So usually we're so familiar with sparse matrix, but there's another class of matrices that we can do fast algorithm or reduce the computation cost, is this dense but has low rank approximation. And then you can, all these things is basically find particular way to find that low rank approximation. This is very constructive many times. You know the kernel, you can do that. But in some sense, we can use, in real computation, we don't know that. We can do well-known SVD or random SVD, try to find. If you know it's a low rank, then random SVD is also very efficient. If it's not low rank, you should not use random SVD. So again, this complexity tells you, again, give you guidance, even it's, it's look like SVD is a very demanding job, but you don't have to do the full SVD. You have to just find the first few, and there you can utilize random SVD to really reduce the cost. So the complexity tell you something. And even nowadays, in old days, when we solve LU equal to F, we always try to emphasize L is sparse. Then we try to develop iterative method because matrix vector multiplication is so cheap. We try to do that. But now if we look at the structure of A inverse, okay, because A inverse, if you think each column or each row, whatever you think, is a Green's function because you put 1 in the right-hand side, all other 0, and you look at what that column is, okay? It's a Green's function. So if you have low rank structure of diagonal, usually people using this hierarchical structure to kind of special indexing of the unknown, so that these matrix have hierarchical called either HSS, hierarchical semi-separable matrices, or H matrix method, directly using this hierarchical low rank structure of A inverse to develop direct fast algorithm. But either iterative method or either this kind of thing, direct solver based on the low rank hierarchical semi-separable structure is mainly for elliptic equation. Once you go to some other type, it may not work. So then we will see some reasoning behind our study. Okay, the first thing we'll present a concrete example is try to say, okay, if I know there's some underlying low dimensional structure, can I utilize that? Okay, so here is a joint work with Sijin Li, Jiwen Zhang at Hong Kong University. Okay, so here, again, I'm not interested in the big difference solving one elliptic equation, then multigrid probably is the best. But I'm trying to solve, because I need to resampling, I have to predict the new solutions, but it's coming from certain family, okay, parameterized by something. Then can I utilize low dimension structure to do this more efficiently or in a different way, I would say. Okay, so again, come back to the things, but the thing is I'm interested in solving a family. Okay, this family is parameterized by these random variables or some parameters, omega in the coefficients and some parameters or randomness in the source. Okay, so I'm solving basically sampling, giving me new omega, a new theta. Can I construct this solution quickly enough? Of course, nothing is free. Here I assume I have data. Okay, so you have many measurements in before, or you have a mini simulation, offline simulation. Now I really want to do a fast online computation. Okay, the true cost most of the time it's you cannot reduce. It's just on the different application. You may have, say, I can afford offline large computation, or I have a lot of data through the measurement. How do I utilize that to accelerate or make my next prediction more convenient? Okay, so this we want to. The key is always dimension reduction. Okay, you reduce the number of parameters in machine learning, or here is a dimension of the problem, Okay, and then if you have done that, that means usually you sacrifice something. That means your representation, your bases are problem specific, but that going to help me to do fast online computation for this specific problem, not for the other problem, but this specific problem. There are many applications we want to do that instead of every time starting from the scratch. Forget about the history, forget about the data. So here we basically utilizing high separability of the underlying Green's function. Basically, say if you fix A, when this changes widely, the solution is not that rich. There's some low dimensional structure. The other one is smooth dependence of the parameter here in this coefficient. And now we know the solution of this PDE depends smoothly on A. Okay, so by this, we know there is a low dimensional structure. So how do we find it? How do we use it? So the idea is quite simple. So if you have a lot of data from this type, from this family of problems or measurements, then you're going to extract the low dimensional structure. That means you extract a basis, problem-specific basis, data-driven and problem-specific basis. Once you have this low-dimensional linear space, then everything becomes how to find the coefficient. Well, maybe 10 dimension, 15 dimension. I just have to find the best 10 or 15 coefficients represented in that basis to a new problem. So immediately reduce a problem from the parameter space to 10 or 15, rather than to the solution of the domain, which is discretized in the whole domain, which is proportional to the grid size. That's a very large dimension. Okay, so there's nothing, again, the thing is you get theoretical intuition or guidance that there is a low dimensional structure. Then you need to find it. Then the find it is if you have kind of sampling of this or measurements, a lot of data for different this realization of omega I or theta I, then you can just do a PCA, okay? You find it a PCA or this is like SVD, but you can do it by random SVD algorithm because you know there's a low rank structure. So you only have to find the leading one. So the random space you project you don't have to be much larger than the leading ones you want to find. Once you have that, as again, every new solution, you just try to find. So this is a solution, the basis you extract out. And here it reduced to a problem to find these coefficients, okay? When a new omega, you try to find what is CK omega. Okay, so this really becomes find the nonlinear map from here, parameter space, to very low dimensional space. This is number of coefficients or the low dimension, the dimension of the linear space you extract it out. So in our case, 5, 10, 15, at most 20, okay? So immediately you reduce this dimension. Otherwise, this is from omega to the solution on the grid, which the dimension is, as I said, the same as the number of total grids. So that's very high, but here it's only to those coefficients. So we can use our old techniques. If the dimension is not too high, the Cassie is not too high, you can think of the data give you some value, the value of C is the vector on this different point of Cassie, and your basically your data tells you for some a scattered point of Cassie, what is the value C? Okay, the next question is how to interpolate, regression, infer, whatever you say, it's all about from known to unknown. You can always talk about this kind of regression or interpolation. How to find if you give a new C, how do I find the C? So you can do interpolation if the dimensions are not too high. As we see, you can even use sparse grid, but when you go to dimension 10, sparse grid is not very helpful either. So you can use moving least square. So just to find if your points are well scattered, you give a new point. I try to find its k nearest neighbor and locally construct a linear or quadratic approximation. And then I try to find that. Or you can say Galerkin construction, this will be the basis, but every time you have to construct the solve a linear system to do that. But that linear system is very small because your dimension is only k, which is 10, 15, so on and so forth. Or after this reduction, you can use fully connected neural networks to approximate this. But I'm trying to say is, because I have effectively reduced the dimension, the neural network is extremely small. It's not like from this dimension to 1,000 or 10,000 or even hundreds of thousands dimension. Okay. So one thing to show is, I give you this is, there are 18 parameters here. So for the change of the coefficient A in this way, there are different scale. You see this epsilon I changing depending on different I. This is different scale, oscillation scale. The F is the sources are located at different places. And if you look, find all the solution and do the singular value decomposition, you can see this is the decay. Okay, this is a log scale. Okay, so you can see up to 10, you already reach very good things. Maybe you should retain 15, that's even more, and so on and so forth. This showing it does have a low dimensional structure. So basically we simulate 5,000, 10,000 solution and put them together to the SVD, you see this. And this is trying to show using neural networks and trying to approximate that map and see how accurate the solution is. It's pretty good, I would say, because it definitely, you cannot write out that nonlinear map. Okay, so here is one way. I'm not saying this is the best way, but just to say this is using just a 5, the dimension reduction is 5, using 5 leading eigenfunction, eigenvectors. This is using 10, using the 20. And you can see its performance, how I say, this is typical performance if to show your training works and your neural network give a good test result. There are also other type of things where the model is even unknown. Here I tell you how A depends on this omega, how F depends on the theta on this parameter. Here I may not. In real model, you don't know the Earth. What is that A? So how should I do? Okay, so in this sense, if we can say, okay, if as long as you allow me to do the measurement, okay, at certain stations, locations, say on the grid, if you tell me the solutions on this, and you allow me to say, when a new, okay, let's say we're trying to estimate earthquake things. If there's new earthquake come in, as long as you give me the measurement at a few specific, I want to choose this location you measure. This location is also choice of location determined from this data. I choose the best location you can measure. Once you measure them, I can have a good reconstruction of the whole earthquake field in the whole domain. Okay, so this is as a few locations. Then I use this 4 location to determine that coefficient C, because I have done dimension reduction. That means that's why for a new solution, I only need a few measurements. I don't need at all grids. The philosophy is very similar because you're still using all the measurement you have. You do PCA, find the leading eigenvectors and the eigenvalues. The leading eigenvector are the basis. And you, using that, you do a QR factorization with column pivoting, try to find locations, M locations, where there are measurement, okay, for the first M vectors, first M eigenvectors, they are most decorrelated. So in other ways, when you do the least square fitting, the problem is not very ill posed. Otherwise, it's basically small perturbation will give you a disaster. So once you use the data, find the basis, and also during the finding the, using the basis you find, you're trying to pick up where the locations it's best, most decorrelated. And then when you have a new earthquake, you just have to measure the earthquake magnitude at those locations, then you can infer the earthquake magnitude at all other locations. So that's basically things. And again, this is example, there's even 24 dimensions and X, Y, F x, y, theta is of this form, has 4 parameters, and you see our results. This is basically what you can do without so basically, if I know the true full field of the new earthquake, okay, this is like Oracle one, and I project it to the basis I have, then that what is the error decay as the number of bases using more and more. And this is, I do not know the exact solution. I only know the measurement at those locations I specify. You should tell me what the measurement, and doing the least square fitting, find the one and compare it to the Oracle one. And this is good behavior, I would say. Okay, oh, sorry, again, time also flies. So I think this comes to a more technical things. Here I told you all the good story about elliptic equation. It's no wonder why there's so many efficient algorithms to do it. But if you transition to something different, where things are very different. So here we're talking about Helmholtz equation in high frequency limit. This is John work with Bjorn-Enquist. So if you look, the Helmholtz equation looks in terms of PDE, the leading term is exactly Laplacian, so innocent looking, so good behave. But there is something on the low order term, which is this, okay? I mean, this is the Green's function, but if in general, this is U, this is U, the right hand has some source. But the only difference is this term. And what I'm interested in is in a singular perturbation domain where the K is large, which means K is a wave number, which means high frequency things. So if you look at the Green's function, when N is equal to 1, if you don't look at the numerator, it's exactly the Green's function for the elliptic equation. It decays the same speed. But the big difference there is a highly oscillatory function, which does not decay with distance, and oscillation increases with K. So we all know this is notoriously difficult to solve numerically. You can say, cite many, many reasons. It's highly oscillatory. It's not smooth in general, but you can say when the coefficient for the elliptic equation is wild, the solution may not look that smooth either, but there are more intrinsic reasons than just this superficial or eyeball behavior. I think this is something already is more intrinsic. So the wave, it's like singular things. It's not like a diffusion. Everything is just a bump, like a Gaussian, okay, decays. Here, there are certain directions things propagate. And if you do 2D and 3D Helmholtz, these directions are infinite, either on a circle, on a sphere. So it's not just two direction in 1D, there's no geometry. There's a lot of singularity in geometry. And when you're talking about discretization, you have to deal with large degree of freedom, whether that's necessary or not. From the oscillatory, it appears yes, but now we're trying to say intrinsically yes. There are no other representations say you don't need a large degree of freedom. And dispersion error, again, due to the propagation in all direction, you want to obey all the dispersion relation. Pollution error, that's really related. It's oscillations at everywhere, and it's propagate. Fast solver, you see there are no efficient iterative solver. For elliptic one, you apply to it, it doesn't work. Direct solver, like multifrontal or HSS, if you for a general median, it doesn't work. Basically, when you push all the unknown to the boundary, that matrix is still dense and no low rank approximation. And what we show is basically try to show from this new perspective, the Green's function is far from highly separable. I think I'm going to need to finish up with this summary of our result because all the later will be more technical, and then I will stop. The main result is trying to say in the old, as I said, one way to see whether you are rich or not is seeing whether Green's function at two nearby locations. Do they highly correlated? If I know a Green's function 1 wavelength from me or 5 meters from me, or I can know pretty well my Green function, or I need to know the Green function 10 centimeters from me in order to know what my Green function is. Okay, so this is decorrelation with the distance. So the first thing we have to establish is still showing the Green's function decorrelates faster and faster. So to Green's function, if they are separated more than a wavelength. So you see the K here is 1 over lambda. So basically it's Y1, oh, sorry. Y1 over Y2 over lambda. So once Y1, the distance, separation distance between two sources are bigger, a little bit bigger than wavelengths, then the Green's function become like orthonormal. Basically, when two vectors are orthonormal, you don't tell me anything of me. They are totally independent, okay? So we try to show how the Green's function decorrelate in terms of wavelengths. So that's the key things to show how rich the Green function is. You're a little bit further away from more than one wavelength, we don't know each other. There's nothing we can comment. There we know a little bit, but I mean, it's very little. And then from this, you know, you have a lot of vectors. You can think of each function as the vectors. They're also orthogonal, okay? They're almost orthogonal to each other. Not exact. If it's exact, then the estimate is very easy, right? If I want to, using a linear space to approximate 3 orthonormal vectors, then the minimum dimension is 3 if you want your error less than 1. So here is almost orthogonal and depend on the distance. So you have to do a very careful analysis to show the lower bound. But the thing is, you should imagine it's rich because there are a lot of independent vectors or almost independent vectors or almost orthogonal vectors. And then we can give explicit this estimate and Mason is sharp to the situations like butterfly algorithm, so on and so forth. Those things you use in practice is a sharp, give sharp estimate. Okay, so I think I used all my time, even my question time, but let me show the most important slide. Oh, there is something we also did just for random field. As I said, I view this as a family of random variables and how to characterize how rich this family of random variables. Then using the correlation, okay, the smaller correlation means this is a rich family, and using smoothness of the covariance function. We only use the covariance function to characterize it. If it's smooth, it helps you. And if the covariance function has some scaling sigma there, which is like the wavelength or like the correlation length, then the smaller the sigma is, the richer is this. So many times when you do uncertainty quantification, our result basically showing if you use 5, 10 dimensions for 2D, you're not approximating any interesting random fields with any interesting correlation. Basically, your random field is very smooth, very highly correlated. But of course, this is saying for random fields as parameterized by the things. If you know your random field is only intrinsically parameterized by a few parameters, that's a different story. But if you're talking about you just give me a random field, and the only thing I know is the correlation length, then I can tell you at least how many numbers of expansion you have to have. The best basis you have, not alone saying, you know, Wiener chaos expansion used certain specific polynomial basis. So what I'm trying to say is, from this, you know what you're doing, whether it's right or not, at least you have some guidelines or insight. Okay, most important slide. Thank you very much for your attention.
Thank you, Hongkai.